Hello everyone, welcome to Shruthis World. In this presentation, we are going to discuss about stability of colloids. As we know, colloids are a state of matter. It has dispersed particles, and this dispersed particles has intermediate size in between solution and suspension. Colloidal stability means there is no particle-particle aggregation in the dispersion between the time of preparation and use. Stability studies include both physical and chemical stability of the dispersion. If a colloidal dispersion is stable, that means there is no particle-particle aggregation in that dispersion between the time of preparation and use. The stability studies include both physical and chemical stability. Physical stability of colloidal dispersion is achieved by maintaining the particles in Brownian motion. Brownian motion can be achieved by two ways. One is to provide electrical charges on the surface of the particle, and the other one is maintaining a solvent sheet around the particle. By these two ways, we can maintain Brownian motion in a colloidal dispersion. And this Brownian motion is one of the reasons for the stability of our colloidal dispersion. Addition of electrolytes or some other ingredients and temperature, agitation, all those factors sensitize the dispersed particles. Sensitization of the dispersed particles that may disturb the Brownian motion. Any disturbance or distraction in the Brownian motion that leads to the instability of colloidal dispersion. As we know, there are three types of colloids. One is lyophobic colloid, the second one is lyophilic colloid, third one is association colloids. Lyophobic colloids are thermodynamically unstable and they may form aggregates. Formation of aggregates in the colloidal dispersion, that is the instability of that dispersion. And in the case of lyophobic colloids, the dispersed particles are charged. The stability of colloidal dispersion is explained on the basis of DLVO theory. You know, what is this DLVO theory? Deraguin, Landau, Verwey and Overbeek theory. That is DLVO theory. This DLVO theory states that the distance between two dispersed particles that influences particle-particle interaction. We know there are two types of particle-particle interaction. One is attraction and the other one is repulsion. According to this DLVO theory, the distance between two dispersed particles, that influences these types of interactions. This theory is also useful to determine the amount of electrolyte required to stabilize a colloidal dispersion or to precipitate a colloidal dispersion. Okay, DLVO theory is useful to determine the amount of electrolyte required to precipitate or stabilize a colloidal dispersion. In colloidal dispersion, the dispersed particles undergo collision. This collision is due to Brownian motion. In colloidal dispersion, particles undergo collision. Dispersed particles undergo collision and this collision is due to the Brownian motion. As I already said, there are two types of interaction, attraction and repulsion. When attraction is predominant in a colloidal dispersion, then after collision, those particles will form aggregates. If repulsion is predominant in a system, then after collision, those particles will remain individually dispersed. After collision, this dispersed particles rebound and they remain individually dispersed. Okay, so there are two types of interaction, attraction and repulsion, and distance between two dispersed particles influences these types of interaction. So, DLVO theory explained the relationship between interparticle distance and the interaction. By using this figure, the scientists explained the stability of a colloidal dispersion. Here you can see this y-axis that represent potential energy and the x-axis that represent interparticle distance. The relationship between interparticle distance and the energy of interaction and the potential energy of interaction that is explained by this figure. The first type of interaction is attraction, van der Waals force of attraction or van der Waals attraction forces. And van der Waals force of attraction depends mainly on the chemical nature and the size of the particle. These are London type forces. We cannot alter this type of forces. The potential energy of attraction is represented by VA. In this figure, you can see VA. This is attraction curve. This down curve represents attraction. This down curve represents potential energy of attraction and it is indicated by the letter VA. This is potential energy of attraction and this force depends mainly on the chemical nature and size of particle. And here you can see repulsive curve. The up curve, this up curve represents electrostatic repulsive forces. Okay, electrostatic repulsive forces or repulsion is the second type of interaction and it is indicated by the letter VR. This electrostatic repulsive forces is mainly depends on the density, surface charge and thickness of the electrical double layer. Okay, this is also indicate the magnitude of zeta potential. Electrostatic repulsive forces also indicate the magnitude of zeta potential. And this curve that represents potential energy barrier or potential barrier. Here you can see a peak and this peak represents potential barrier or net energy of interaction. Actually, this net energy of interaction is the algebraic addition of the attractive and repulsive curves. Okay, it is the algebraic addition of the attractive and repulsive curves that represent the net energy of interaction. And this net energy of interaction is represented by the letter Vt. The net energy of interaction is represented by or it is indicated by this letter Vt. Now let's see what are the conclusions we get from this figure. This is primary minimum and this is secondary minimum. What is this primary minimum and secondary minimum? What are the indicates? Primary minimum is a sign of precipitation. Consider two particles in a dispersion are present very close to each other. In such a case, atomic orbitals of such particles will overlap and penetrate each other. That leads to the formation of aggregate in that dispersion. And such type of interaction indicate a rapid rise in potential energy that represent primary minimum. Actually, primary minimum is a sign of precipitation. Here you can see primary minimum. This is primary minimum. Here two particles are present very close to each other. The distance between two particles is very less. One particle is present here and the other one particle is present here. So the distance between these two particles is less. Because of this, atomic orbitals overlap and penetrate each other. That leads to precipitation. That is primary minimum. Like this, atomic orbitals overlap and that leads to stronger attraction. Because of this strong attraction, aggregates will form and they precipitate. That represent primary minimum. Here you can see our net energy of interaction or potential energy barrier. It is a sign of stability. Okay, this net energy barrier indicates the stability. If the particles are present intermediate distance, then appreciable repulsive forces operate there. So these repulsive forces prevent the aggregation of dispersed particles. So there is no aggregation that indicates the stability of the colloidal dispersion. The next one is net energy peak. Here you can see net energy peak and this is potential energy barrier or net energy of interaction and this peak represents stability. Okay, this peak represents stability. If the colloidal particles are in intermediate distance, then appreciable repulsive forces will operate there. And this repulsive forces prevent the aggregation of the colloidal dispersed particles. There is no aggregation that indicates the stability of the colloidal dispersion. We know the potential barrier or net energy of interaction is the algebraic addition of the attraction and repulsion curves. If the potential energy barrier is high, that indicate there is Brownian motion. Brownian motion is there in the colloidal dispersion that indicate the stability of the colloidal dispersion. If the kinetic energy of the colloidal particle that surmount this potential energy barrier, then aggregation will be occur. Okay, keep in mind that if the potential energy barrier is high, that indicate the stability of the colloidal dispersion. This peak, here you can see the peak of this curve, and this is represented as maximum potential, and this represent Vm. And stability of a colloidal system is defined by the height of the maximum in the potential curve. So this peak represents better stability of the colloidal system. Now move on to secondary minimum. Secondary minimum is a sign of aggregation. If the colloidal particles are present in long distance, one particle is present here and the other particle is present here. The distance between particles is high as compared to the first case. Here the distance is about 1000 to 2000 angstrom. Still some kind of attractive force exists there. That results aggregation of particles and that leads to the aggregation of particles. That is secondary minimum. When the kinetic energy of the colloidal dispersed particles that surmount this potential energy barrier, at that time coagulation occurs. Okay, at that time aggregation occurs. That leads to the instability of that colloidal dispersion. Coagulation of colloidal particles may be accelerated by two ways. One is by reducing the height of this potential barrier. If any reduction in this potential barrier occurs, that leads to the instability of the colloidal dispersion. If the potential energy barrier is reduced, then aggregation occurs. Coagulation of colloidal particles can be accelerated by two ways. One is by reducing the potential energy barrier, and the second one is increasing the kinetic energy of the colloidal particle. By these two ways, coagulation can be accelerated. If coagulation is accelerated, coagulate or aggregates is formed in our colloidal dispersion. That is the instability of colloidal dispersion. Once the kinetic energy of the colloidal particle is surmount this potential energy barrier, coagulate is formed in the dispersion. That is the instability of the colloidal dispersion. So by using this figure, we can explain the stability of a colloidal dispersion. This is about stability of colloidal dispersion. Hope you all understand. Thank you.